All right, Math 170. We are on the last section of Chapter 4, 4.5. We're going to go over the substitution rule, or as I like to call it, USub. It's a little easier to say. So to kind of set this up, I want to start off with reminding us that when we dealt with differentials, we used to think of dy dx as a ratio of two numbers. So since we are dealing with the notation as a ratio, it's okay when we kind of take the derivative. Let me see if I can start you off. Here's an example really quick. So let's say like y equals 3x. And then I ask, how about we find dy dx? And so it's true. You're saying, oh yeah, derivative of 3x is just a 3. But since these are now ratios, these two items, it's okay to multiply both sides by dx. Maybe we want to get rid of the fraction in a sense. So what happens is we can now rewrite this as dy equals 3 times dx. So we're going to kind of be doing that throughout the section. Another idea, let's say I have u. Sometimes the variables switch up on us. So let's say we have u equals 5x cubed. So if we wanted to find the derivative of u with respect to x, well, what is that? 3 times 5, 15x squared. But again, since we can think about these two items, du and dx, as a ratio of differentials, it's okay to multiply both sides by dx. So what happens is we can now rewrite this as du equals 15x squared times dx. This is going to be the first idea of when we're using USub. So as in the last section of 4.4, we had ended on an example where we kind of reminded us like, hey, you know, we could do example 1 that we just did. I think it was, I think it was the last example in 4.4, I think. Yeah. We did this by multiplying everything out with FOIL and then integrating each term, and it's a polynomial. But last section we kind of say, isn't there a better way we can do this? So what I like to kind of always go with, and I'll write it out as a rule of thumb. So it's kind of like what to do if no one tells you what to do. Whenever you have a product of two functions, so if you kind of notice, we have a function, 2x, times another function, x squared minus 1 squared. So whenever you have a product of two functions in the integrand, I think that it's a great idea to always try USub before attempting other techniques. Because most of the time, the USub will set you in the right direction. So, you know, how do we do USub? We're actually demonstrating it. They want us to use it to evaluate, even though we don't have to. But let's look at this a little more in depth. The first thing I want to pay attention to is kind of anytime you see something more complicated taken to a power. We'll start off with that. So I see x squared minus 1. It would be so much nicer if that was just a single x, or x squared. So what we like to do is we'll use a USub, which meaning we're just going to substitute the x squared minus 1 with a variable u. But when you do this, so I'll kind of write that out to remind us, and maybe I should kind of point to it as opposed to underlining it. Sometimes you get confused that that's division. Once you understand that you set the u as x squared minus 1, then you take the derivative of u, kind of like what we were doing up here. So we could kind of say, well, all right, then du. So, whoops, let me write that down. So derivative of u with respect to x, what do we end up getting? It's 2x. And then we kind of notice, oh yeah, we had that idea of the two differentials. If you have a ratio of two differentials, you can multiply both sides by dx, and so you end up getting 2x times dx. And once you make this substitution and then you calculate the corresponding du, you're going to want to find a substitute for every component in the integrand in terms of our substituted variable u. Let me write that a little nicer, in terms of u. So what I'm kind of looking at is, well, I already know the highlighted part, x squared minus 1, that is a u. My issue is seeing all the other items that have x's in them. So we kind of look at this a little more carefully and we notice, wait a second, there's an extra part of 2x, and there's also a dx. Well, the idea of calculating the derivative of u with respect to x is to recognize that it does appear in the integrand, this 2x dx. So what I could kind of rewrite this as, just so that you have an idea, we'll start off. Here's the original problem, x squared minus 1 squared dx. Just rewrite it so you can see this a little bit better. This is equal to, if I rewrote it, so I have the x squared minus 1 first, and I have the 2x dx. Now we could kind of see that when we made our substitution, we ended up having this part be u, and this part is du. So that's really, really powerful because we just broke down something quite complicated and we rewrote it. Let me kind of write it nicer. Don't forget that the u was taken to the power of 2. We rewrote it into a nice power function for which we can integrate quite quickly. So if I can kind of see this, we would say, well, let's integrate this, might as well. If we integrate power function, what that ends up being u cubed over 3. And don't forget that plus c, that's still part of the issue. So we can integrate as usual, but whenever you make a substitution, kind of like what we did in algebra, you have to make sure that the final answer has to be in terms of the original variable. So final answer should be in terms of the original variable. In our case, it was x. So just go back and say, well, what did I make u equal to? U was equal to x squared minus 1. But now, when that gets substituted back in, it was all over 3. And then we have a plus c. Plus c ends up changing a bit, but again, they end up being constants no matter what they absorb. So technically, we might call this C1 and then it turns into C because we resubstituted for X. But at this point, we kind of wave our hands a little bit and say, yeah, don't forget. Just don't forget to add the plus C and you will be good to go. We'll circle that a little nicer for you. Now, if you're not sure if you did this right, you could check a little bit on the side, not as part of your work, but you could say, well, what is the derivative of x squared minus 1 cubed over 3 plus c? And you kind of notice, well, derivative of that more complicated expression, hence the need for the u substitution, was at 3 times x squared minus 1 squared, still all over 3, and derivative of a constant is 0. But you have to remember that when you take the derivative of something more complicated than just an x, there's a chain link we attach on. So what ends up happening when we simplify, what if the 3's divide out? And we end up getting x squared minus 1 squared times 2x. And if you go back and look at your original integral, oh yeah, it's the same. So this is a really nice technique that we can utilize when we have, a lot of times we'll see it when we have powers. And I think the number one idea that I always look for is if I have something raised to a power that's a lot more complicated than just an x. So it's kind of like an extension. So let's see, having said that, let's see if we can demonstrate that in example 2. And this would be a great candidate for USub because yeah, there's no chance I ever want to multiply anything out to the 20th exponent. So what I'm kind of noticing, I'm saying, okay, 3x squared doesn't look horrible, but I know it's a product. So I have a product of 2 functions. I look at what's taken to a power or maybe what's underneath a radical. We don't have a radical in this case. But I look at this expression right here. It's taken to the power of 20. And I kind of say to myself, you know, wouldn't it be nice if I just had a single variable taken to the 20th power? Life would be a lot easier. So that, my friends, ends up being our u. So u, I always want to have the scratch work off to the side, either to the left or to the right of the problem. I'm going to indicate that my u is x cubed plus 15. Now, once you have u down, you're going to say, okay, let's calculate du with respect to x. So you're taking a derivative, so that becomes 3x squared. And then you're saying, okay, well, I'd rather have it in terms of du, so multiplied by dx on both sides, so I have 3x squared times dx. Now, eventually, you'll get really good at this because you're doing this quite a lot. And you're going to eventually just understand that, oh yeah, we skip down to this step once we find the derivative. So now what I try to look for is I'm going to say, well, I know I see my u. I'm going to look at the rest of the factors in the integrand and see if it's part of the du. So I kind of look at the 3x squared and you kind of notice, okay, that's there. And I also see that the dx is also there. So right away, what's interesting is I can do all of the replacements at once. Let me see if I can erase that just a little bit so you see that there was still an integral involved. So I'm going to replace everyone. Now keep in mind that it was the u that got replaced and it was u to the power of 20. We did not change that at all. The 3x squared dx actually ends up being just our du. And that's what we're supposed to have anytime you integrate something that has a u in it. See if I can make sure I see that absorption there. So now, this is so much nicer to integrate. We just take our time and we say, well, we're integrating this. What are we going to have? U to the 21st over 21. And what are we missing? Everyone, we got a plus c. Yes. And then the very last step is to say, okay, well, we didn't start with u. We started with x. So if you start with x, you better end with x. So instead of u to the 21st power over 21, we're going to replace the u back with x cubed plus 15. And we now have the answer to our integral. So it's quite nice. They come out really nice. You don't have to worry about multiplying anyone out. And you end up getting an answer that you'll notice, oh, there's some patterns along. So you'll probably practice a few of these. You start feeling good about yourself. And all of a sudden, you know, like you're going to come across a problem that doesn't quite lie out as nicely as the first 2 examples we've done. So I'm not going to lie to you. Not all the USubs are as easy or as nice. I don't know if they're easy, but they're not as nice as example 1 and example 2. So if I kind of look at, let's look at part B, and you kind of notice like, oh yeah, I mean, it's almost the same as part A. I think the only thing is that we have a 3 going on that we're missing. So you can start off, you're noticing, oh yeah, it's function times function. I'm noticing more complications taken to a power. So that's no problem. We can call this u. U equals x. Let's write this a little nicer for you. u equals x cubed plus 15. And then we realize, oh yeah, well, if we call it u, then we take derivative of u with respect to x. So du is 3x squared times dx. See what I said about skipping a step? And then what you end up doing is you're saying, okay, I go through the problem and I'm looking at my du and I notice, well, I do see the dx. That's good to go. That's already in there. I do see an x squared. That is good. But I have to pay attention to the fact that I'm missing, the original problem is missing this. And it's a factor that it's missing. So we kind of have to pause a little bit and we say, okay, Well, we kind of go through and say, well, there's a way of, around this. It's actually missing just a factor that's a number. So that's going to be convenient to us. So before I maybe even show you this, maybe I'll have you go back and see if you can figure out the rest of the problem. I'll walk you through a different example and see if you can apply it to part B. So let's see. Let's go to example 3. And let's see, I'm going to show you a couple of different ways to approach problems like this. And let's see if we can kind of reconvene and look at part B in a second. So same idea. You kind of notice, well, they've all been products of functions in the integrand, x times x squared plus 5 to the 7th. And, you know, even taking it to the 7th power, I know we could do it, but we're not too excited about multiplying it out. So right away, I'm kind of seeing like, oh yeah, I can make a USub. I'll try it. U is x squared plus 5. So then when I calculate the derivative of u with respect to x, that was 2x, and then multiply that times dx. And so I kind of just scan my integrand and I notice, okay, I see the x as a factor. I see the dx as a factor. And then I notice, aha, I'm missing this. And so when you notice you're missing a number factor, so it's a constant factor, there's 2 ways to handle this. I'll start off by, I'll start one way. I think this is the way I kind of promote because I think it's the first way I learned it. So I guess it's just kind of more natural to me. But what I could do, options. Either or will work. One of the things you can do is you can introduce, it's a nice math trick we end up doing, introduce 2 to the integrand. But when you introduce 2 to the integrand, you can't just do this, you know, at will. You have to do this logically with mathematics. So when you introduce 2 to the integrand, you're actually going to introduce the 2 by multiplying the integrand by 2 over 2, because my friends, what is 2 over 2? Is equal to 1. And it's okay to multiply anything by 1. It never changes the function. So that's one of the ways. So let me show you really quick. So what do we have? Our function itself, x times x squared plus 5 to the 7th, the dx. And so what I end up doing is if I notice a number factor is missing, I want the 2 here, but I have to multiply it by 2 over 2. So that way it wasn't really changed other than we attached a factor and divided by the same number. Those are some nice math tricks. Multiply by a number, divide by the same number, and sometimes we do the add 1, subtract 1 eventually. So now what you can go and you can say, well, we've got it. Now I'll see if I can highlight. I've got my u. I've got the dx, the x, and I have now the 2. I'm very happy about this. So what ends up happening at this stage is you can do the substitution, but just leave whatever factor is there that was not originally in your du. So now we have the du all there. That is, just so that you know, it's 2x times dx. So when we rewrite this a little bit nicer, keep in mind that the 2 is still hanging out in the denominator. And I'll rewrite it just so that we can see this a little bit clearer. If you like, when you first start off, it's not a bad idea. It makes sure that you see everything there. So we have this 2x dx. So again, one more time, we end up having the u and the du. So now we just clean it up just a little bit. I have a factor of 1/2. I'll just factor it out. And I'll do the substitution. So I should have u squared times du. And now a whole lot nicer. Now what we can do, I think I'm running out of room, but I'll go sideways for you all. I have 1/2. Whenever I integrate, I should have the u cubed over 3, and then we have a plus c. Wait, did I have, oh my goodness. I would probably blame you if you were in my class, but no one stopped me because no one can stop me except for the dog, but she wasn't watching. So let's look at this one more time. Class, was that a 7? And class, why did I write a 2? Probably because I'm on autopilot. It happens sometimes. So let me make sure I correct that. I apologize. But now you know I'm not a robot. So, okay, so just make sure it's not u squared that we're dealing with. It's u to the 7th, which if it was u squared, we probably would have just multiplied it out. So that justifies my answer a little bit better. So let's clear this up a little bit. If you integrate u to the 7th, we end up getting u to the 8th over 8. And so if you notice the 1/2 was still there, what we want to do is maybe clean this up a little bit. I'll move sideways just because I don't want to crowd the next page. So I should have u to the 8th over 16 plus c. But remember, if you started with x, you got to end with x. So the final step is replacing your u with whatever you substituted it with. And in our case, u is equal to x squared plus 5. So we should have that over 16 all to the 8th and plus a c. And now we have a technique to help us whenever we're missing a number factor from the integrand. So that is one way to go. Sometimes that way might work nice most of the time with the numbers. And then another way that a lot of people like as well, I kind of picked this up later on. And it's really the same idea, but sometimes it speaks to you a little bit better. So another option, just in case, doing the same problem over again. So the other option would be, why don't you try to solve for what is already in the integrand? So let's see what we're looking at. Let's go back and say, well, what's already in the integrand? Let me restate this. On the side, we had u equals x squared plus 5. Then we had calculated du equals 2x dx. And we noticed we were missing a 2. So what I'm interested in kind of understanding is what's already in the integrand. And I will unhighlight this so that we see this. There's an x times dx. So if we took this part and we say, well, we already see that in the integrand, and we solve it for that part. So that means you're isolating it by dividing both sides by 2. What we end up getting, and you kind of see like, oh, it all relates later. We get 1/2 du equals x times dx. And now what you can do is you can go back and replace it. So now let's rewrite it over again just so that we kind of can see. Here's the original integrand, x times x squared plus 5 to the 7th, everyone. Aha. So now what we can say is we already have a replacement. So sometimes, you know, if I would have learned this first, I might have gone with it and that would have been a little bit happier for me. I have x dx already. And I know that this part right here is u. So now all you have to do is replace it. You can say, I can replace this all with 1/2. And if you feel like writing it over, if this is something that will help you see it better, I'll do this for sake, so you guys can really see what's going on. Again, I have the u, and I have the part of the du, the x dx. So what happens? Again, remember we had u to the 7th, no problem there. But x dx is actually 1/2 du. Sorry, my left hand switched pages. And my friends, check it out, it's the same thing we got when we introduced it to the integrand. So I don't know, I mean, when I look at this a second time, I might like option number 2 better, because I could kind of see what to replace. Makes a little more sense. But I guess it's just because, we're stuck with me learning this option number 1 first. So I guess that's usually what I end up doing. But feel free to approach it anyway. So by the way, when you do integrate it, we're getting the same thing. You do the 8th over 8 plus c, and I can't leave any problem unfinished, So then you replace everything and everyone's happy again. That's what x squared plus 5 to the 8th over 16, and then we're adding a c. We're getting the same answer no matter what. So 2 options if you're interested. The number 1 key is that the factor that is missing is a constant. So that's kind of what we'd have to do if we ever run into problems like this. And it happens quite often after you do the first few problems in the section. So now, I think I've left you with enough experience so that you could actually try this one on your own. You guys notice that, okay, I have my u equals x cubed plus 15. No problem there. I calculated du, and I noticed that the original problem is missing this number factor, which is the 3. So take some time. You can pause the video and see if you can try it and see what you get. See if you get the same answer, either looking at number 1 or number 2. Maybe I should just not even give the answer, because then sometimes you'll just nod your head and say, yeah, I got it. So maybe you want to check back with me and see if you get it. Feel free. Okay, so let's look. Let's look at a little bit more. I guess this would happen. This type of problem could happen somewhat after you've done a lot of introducing constants to the integrand. So yeah, a little practice there. Some USubs end up being a little bit trickier. And here's an example of what's actually happening here. So I'm kind of noticing the radicals, they show up again. And no problem, we've dealt with radicals before, and we kind of know maybe the number 1 thing we end up doing with radicals. A lot of us will say, I don't like to see the radical. I'd rather see it rewritten as an exponent. So rational exponent still got the dx. Well, what you've just done at this point is you're saying, okay, well, I've kind of converted it to somewhat of a power function. And then the issue is that the base that was taken to the power is a little more complicated than just an x. So you kind of see that portion right there ends up being what our u is. So u is x minus 1. And so you still say, okay, well, I'm going to try to calculate du. Derivative of x, 1 is just 1, and then we have a dx. And you don't have to write the 1 if that's something that bothers you. I'm just trying to help you out. But when I look at this a little carefully, I'm noticing, wait a second. I'm looking at my du right here, and I'm saying, well, I've got the dx. I'm good to go. But See how I have an extra factor hanging out? My du needs an x. And this is an issue. When you have an x, we're not allowed. We cannot introduce variables. Or I should say variable factors to the integrand. Because when you try to introduce them, what happens? You would say, oh, I need an x over x. But the issue is we don't know that x is not 0. And so if x is 0, we've just made, how do you say, math jail? What do we call it? Illegal step in mathematics. So x could be 0. And that is why we have the issue. You're never allowed to divide by 0. And we've been doing that a lot. So there is one extra trick here. Okay, so here it is. So kind of like a way around this. Instead of trying to introduce the x, why don't we look at this a little bit nicer and say, well, we have things in terms of u. Why don't we solve it for x and see if we can come up with another expression that makes it a little bit prettier? We'll see. Might not be prettier, but we'll try. So we have u equals x minus 1. We can manipulate this substitution any way we would like. So let's solve it for x. So if you solve for x, you have to add 1 on both sides. Yep, we do. So we end up getting x equals u plus 1. So now what we can kind of play with is say, let's start over. And like I said, that's kind of what happens when you integrate sometimes. You go down a path that leads you to a dead end, and then you try something else. It'll get you used to calculus too. So we're going to look at this a little differently, and we're going to say, well, we now have a substitution for x. So instead of x, I'm changing it to u plus 1. Now, check this out. You're doing this everywhere, and I probably shouldn't have erased it, but I'll do this. I still like having the 1/2 power as the exponent, so I'm going to keep that in there. But now, what was x again? X was u plus 1. But what's already there is a minus 1. And we still have dx going on. But, by the way, if we replaced u with x minus 1 or x with u plus 1, we don't call it dx anymore. We call it du, because du and dx mean the same thing. That's kind of nice. But check this out. Check this out what this does. We still have the u plus 1, but u plus 1 minus 1 is now u to the 1/2. And you might be thinking, didn't we just switch it around so it looks more complicated? And in a way, it does look more complicated, but what I would like to point out is the stuff that is more complicated is now only taken to the power of 1. And so we don't have to worry about having it stuck underneath a 1/2 power or anything more complicated. So this is where we utilize a little bit of algebra. And we notice, oh, well, that's like a monomial times a binomial. So you can do distribution, kind of turn it into a power function. So what do we have? Is we have u times u to the 1/2. So what do you add 1 plus 1/2? That gives you u to the 3/2. Times 1 times u to the 1/2. Oh, that's plus. We end up getting u to the 1/2. And we're still taking it with respect to u. So a slightly different version of a USub. We had to manipulate our U substitution to kind of get us a better idea of what the function could be. And now you have a sum of 2 power functions. So these are quite nice. You're probably used to this by now. If you want to integrate it, let's do it. I know they're fractions, but we've been doing this for a while. You add 1 to the power, you divide by the same thing. And the same idea with this next one, we add 1 to the power, divide by the same thing. So when we integrate, once you get rid of the integration symbol, don't forget your plus c. Still very important. I know we tend to forget that. So let's clean this up a little bit. I want to take this, let's see, 3/2 plus 1. That ends up being 5/2. So once I kind of figure out what that is, I have a shortcut. If this is 5/2, we end up having 2/5 u to the 5/2. Take time if you need to, no problem there. And I know this ends up being 3/2, 1/2 plus 1. I've been adding these fractions quite a bit. So if we do that, what do we have? U to the 3/2. But if I know this is 3/2, I'm really multiplying everything by 2/3. So I want to clean this up just a little bit. Don't forget, we still have that plus c hanging out. And what's the, yes, we have to replace it. That's true, Laika. She noticed that we have a u, and remember, if you start, yes, she said u. You remember, if you start with an x, you've got to end with an x. So what is that again? What do we have to replace, Laika? All right, so thank you. I'm glad you listened to me. So we're going to replace this. I still got the 2/5, no problem there. But instead of u, remember, I can't get her to say this one. We let u equal x minus 1. So we have x minus 1 to the 5/2. And then again, we have plus the 2/3, x minus 1 to the 3/2. And again, don't forget your plus c, otherwise you end up losing points. All of the math teachers get upset. Now, you might be wondering, do we have to rewrite it as radicals? And it's possible. At this point, since I'm not doing anything with it, I would say it's okay to leave it as a rational exponent. But if you feel inclined to, you want to convert everything back to radicals, that's fine. I don't believe anyone's going to get mad at you. I think the only time they get mad at you is if you make a mistake converting back. So just kind of be really careful. So that is very, very, very fun. Let's see if we can play with this one more time. We'll try this idea. Keep in mind these types of problems, they kind of approach us towards the end of the section. So you'll probably have a lot of experience already kind of working through some of the earlier examples so that you'll be prepared when they come to challenge you. So let's look at this. Let's look at example 5. We're evaluating 1 over 1 plus square root of x to the 4th power with respect to x. And you kind of notice, okay, this part's complicated. It's taken to a 4th power. I would love if it was just a single x. Also, what might be interesting to you is you're saying, maybe we don't like having powers in the denominator. We've done this before where we say, if it's a power in the denominator, why don't we rewrite it so that we end up having a negative exponent? That tends to be a little more user-friendly, not only when we're integrating, but when we were taking the derivative as well. Okay, so you kind of rewrote it so it's in terms of a power. And so that kind of gives you a heads up of, all right, well, we could kind of talk about what u would be. Now, to me, it looks like it's going to be 1 plus square root of x. Complication there. So once you identify who the u will be, we kind of go through the process and we're going to calculate derivative of u with respect to x. And so we can go through, well, the derivative of 1 is 0. Don't have to worry about that. But we do have to worry about the fact that it's a derivative of a radical. And so if you felt inclined to, you can say, that's like x to the 1/2, whatever works. So if I took the derivative, it would be 1 over 2 times x to the negative 1/2 times dx. And then if you're kind of playing with it, you're saying, well, maybe they get a little prettier. What do we end up having? 1 over 2x to the 1/2 times dx, or 1 over 2 radical x dx. Sometimes you're so used to taking derivatives of square roots by now you could have skipped, there's no problem. But now when I'm looking at it, what's the point of us doing all of this is we're supposed to take what we find for du and we're supposed to compare it to what we see in the integrand. So right away, I'm happy I see a dx, that's fine. But you notice how we don't see a 1/2. We're missing a 1/2 from the integrand. And that's fine, it's a constant factor. But what is the issue? You care to add anything, Leica? No. Well, if she could talk, she would say the issue right here is that variable. So this variable expression, variable factor, is not in the original integrand. And so whenever you kind of notice a variable's not in the integrand, we're going to use our trick one more time. And this might be another way to approach this. This is kind of why I had to show you both options, because it tends to be part of it. One of my tricks, which ends up getting us out of this mess, is we're going to solve for dx and see what we get. So let's see. Let's write this out one more time, just so that we see this nicely. Remember, du was equal to 1 over 2 radical x dx. So if you solve for dx, what are we doing? Multiplying by 2 radical x on both sides, just so that we understand this. And if we do that, we should get dx equals 2 square root of x times du. Now check this out. We do have something with a radical in it. So I'm kind of looking at this a little bit more carefully, and I'm saying, I still have issues here. And I like the 2. I'm okay with the 2. I'll figure that out. What I'm more interested in, where's my color? Here we go, right here. This is still the issue. Even if we replace, we can replace the 2 inside, that's fine, it's a constant. But I'm gonna have to take this part right here, and I'm gonna have to rewrite it in terms of u. We're not really happy when we see the x. So take this, rewrite in terms of u. And remember, if that's the case, what did we let u to begin with? So we have to kind of look back at our work, and that's why it's so important to write all your notes down on the side and be organized. U is equal to 1 plus square root of x. So now you can kind of say, oh, well, we see a square root of x here, we see a square root of x here. So if we were to kind of say, what if we solve the substitution for the square root of x, just so we know what to replace it in, we'd have to subtract 1 from both sides. So we would get u minus 1. So now, this is what makes it a little bit more prettier. Dx can be replaced with, and I'll write it over here. So now dx can be replaced with 2, not times square root of x, but 2 times u minus 1. And then don't forget that there was a du there. Now you might not be able to see that, so let's shrink it down. What was I trying to do in the first place? Take this part, dx, and now replace it with this part. And if I can do that, I'll blow it back up again so we could all see this in a nicer version. So I can say, all right, what did I call the 1 plus square root of x? I called it a u. But I have u to the negative 4 power. Dx now becomes 2 times u minus 1 times du. So it's kind of a little bit of a trick on not just solving for what we need it to be, but we also utilized option number, where was it? Option number 2 kind of gave us a little way, it's a little nicer. I welcome you to try a few different ways and see what works best. Mine might not mesh with yours, and that's totally okay. The more experience you have, the better off you are at trying what works for you and what doesn't work for you. So I'll write this a little smaller so I can fit stuff on the page. I have a feeling I'm going to run out of room. I do write a little larger. Let me write this over again. I know I had shrunk it down, but now I want to make sure you guys can see. Okay, so this ends up being u to the negative 4, and then dx one more time was, see my short memory, 2 times u minus 1 times du. Okay, here we go. 2 times u minus 1 times du. Now everything's in terms of u. It might look like we are making it more complicated, but we'll notice that the more complicated part, this u minus 1 is only taken to a power of 1. So that's going to be very nice. Let's clean this up just a little bit. Well, we like cleaning everything up. I'm going to take that constant out right away. Now I've got u to the negative 4 times u minus 1 with respect to u. Now there's more than one way to approach this. You can go and distribute the u to the negative 4 in, see what we get. Sometimes I kind of like that. You could also rewrite the u to the negative 4 back in the denominator and use some of the tricks we were using. Was it this section or was it the last section? Must have been the last section where we divided by a monomial. So like I said, different ways to approach it. I'm going to distribute the u to the negative 4 in, make it a single polynomial. So we do have 2. This portion becomes, now we got to just be careful though. When we multiply with the same base, keep the base and add the exponents, negative 4 plus 1 gives us negative 3. Got a minus sign. We still have u to the negative 4 now. So at least we have a difference of 2 power functions in a sense, still with respect to u. And so now this is more user-friendly. We can say, oh, well, we can integrate these with a nice power formula. So we have a difference. What I kind of remind us to do is kind of say, well, I'm integrating this first piece right here. That's what, u to the negative 3 plus 1 over negative 3 plus 1. I have the minus sign. Then this second piece, maybe I'll do that in blue. I have u to the negative 4 plus 1 over negative 4 plus 1. And what do we need, everyone? You are right, a plus c. Do not forget that ever. So clean it up. So we have 2. That's on the outside, no problem there. This ends up being u to the negative 2 over negative 2. So got a minus sign. And this will be u to the negative 3 over negative 3. And at this point, if you're inclined to do so, constants being factored out is not too big of a deal. You could kind of leave constants factored out, but sometimes you'll see that when you distribute the 2, maybe stuff will cancel out with the fractions. So I might do that. Distributing the 2, you'll notice that you end up getting negative u to the negative 2, that the 2's divide out. Negative sign does not. Now we have minus a negative, so that ends up being plus. And if you're distributing the 2, you're going to have a 2/3. U to the negative 3, and what are we missing, everyone? A plus c. Don't forget that one. Now we're feeling pretty good. A lot of times people do not like it when you leave negative exponents, and a lot of times the web assign marks you wrong. So at this point, you can say, okay, let's change it. Using exponent laws, what did we end up having? 2 over 3u cubed plus c. So right now it's starting to look pretty, but my friends, what is the rule of thumb? What variable do we start with? If we start with an x, we must end with an x. And right now we have u's. So don't forget at the end, resubstitute. And what did we let u equal to be in the first place? That's why we did all this work. It's 1 plus radical x, 1 plus square root of x. So we take those u's, replace them. I'll leave some space for you. Don't forget that plus c. If we do, we get it wrong. So 1 plus square root of x, 1 plus square root of x. And that is now the answer to our indefinite integral. That's a good one. So very, 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 very nice. So again, this is something, to me, I feel like this is a problem at the end of the section. I really like to go over them because that way when you approach it, you have something to look at. But again, by the time you get here in the section, you've been doing all the homework, you'll be prepared. May seem a little overwhelming at first, but I have a feeling you'll be fine. So just kind of like rules of thumbs before we kind of move on to the next part of this section, which is just a little extension. When we're in Calc 1, that's the class we're in right now, a lot of times we have kind of some strategies. So maybe I'll kind of maybe plant the seed in your mind right now. So what are we in, Calculus 1? I used to call you guys, your Math 170 for us. When you have the integral of something that doesn't look like fundamental properties, there's two options we can kind of play with. Remember, I'm just summarizing everything we've ever learned. We could either use algebra to simplify or trig identities. If it's, quote, nice to do so. Or what we can then do is use USub. That's our favorite technique. So if you're ever stuck, try USub. That's the whole idea of our class, Calculus 1, when we integrate. However, when we go to Calculus 2, what are we, Math 190? If we're in our school. What you're going to learn in Calculus 2, you're going to expand on techniques of integration, like a lot. So Math 190, there's like 10 different techniques for integrating. Okay, so if you have the integral of something that doesn't look like fundamental properties, you're going to learn a lot more integration techniques, or you will use USub. So moral of the story, don't forget about USub because it comes up quite a bit. So it's kind of getting us in the mood for the next class, which is coming up sooner than you think. So exciting. Now that you have some techniques under your belt, I want to point out that you will end up having to integrate definite integrals that are more complicated than the ones we were dealing with in the last section. And what happens to happen, I don't even know if that was a correct way to say that, but what ends up happening is you end up being able to use the USub and you incorporate this in the limits of integration. So I'd like to show you a couple just so that you can kind of get the hang of it. And what's kind of nice about the definite integrals is for the most part, you can use your TI to check yourself. However, if they ever ask for exact answers and they want you to show your work, then you do have to show your work. So let me see if we can recall one last time. Don't forget, reminding us, what do we have? Definite integrals. And with the definite integrals, I want to say the upper limit for x, right? I'll point to that. Is 2. The lower limit for x is 1. And how do I know there are limits for x? Well, check it out. The dx is the heads up. So this differential right here always tells us what variable we're integrating with respect to. You're like, I knew that. Well, good. I'm glad you knew that. But I'm really making sure that the reason why we know that these numbers stand for x has to do with the fact that you're integrating with respect to x. More important to pay attention to this later, if you go to Calc 3, what is that? Math. I don't remember what number that is, but I do know it's Calculus 3. What's going on is that you're going to be integrating with respect to different variables, and there'll be other variables inside the integram. So it's really important to pay attention to that part. So by the way, you know, we've done this before. We know that if we take the integral from 1 to 2 of x squared dx, what do? We integrate like normal. That's x cubed over 3. But we evaluate that from 1 to 2, where we're replacing x each time. So fundamental theorem of calculus, FTC as the cool people call it. What is that? 2 cubed over 3 minus 1 cubed over 3. So in the end, what do we have? 8/3 minus 1/3, which gives us a 7/3. Just kind of a quick refresher. Our favorite function to integrate is the x squared. So what happens in the last part of this section is you start noticing, I have more complications. I look at my integrand and I notice, hey, super complicated. But I now have techniques to deal with complicated integrands. I'm using USub. And when I use USub, we'll do that. Let's take that into consideration. You kind of notice, oh yeah, it's something taken to a power. Now I know my u should be that x squared plus 1. That's fine. I can find my du. That's 2x times dx, taking the derivative of u with respect to x. So then you could kind of say, oh yeah, well, we have the dx, we have the x, and what are we missing? We're missing the 2. That is correct. So if we're missing the 2, we can either solve it for dx, what we see in the integral, or we can replace it right away. So whatever you prefer to do, I'll switch it up. I can solve for the x dx, and if that is the case, I get x times dx equals, divide by 2 on both sides, it's du over 2. So I switched it up on you, but it's the same thing. So now when you're kind of replacing, you're kind of saying, well, if I go through all of this, x times dx, x dx is now du over 2. Write that in green maybe. And then I'll write the 2 in the red, mine as well. And then x squared plus 1 is really what u to the, well, x squared plus 1 is u, and then we have it to the 5th. So my friends, what ends up happening? What do we factor out the 1/2? No problem there. We end up trying to integrate with respect to u. But here's the issue. If you have a definite integral, and you know they're hard to see sometimes, when you integrate, what's going to happen is that these limits of integration will change because they're in terms of a different variable. So there's 2 ways to go here. What you can do, and I like this way sometimes better, kind of depends on what I can get for myself, but I still need to attach limits of integration somehow to this statement. If I already know what u is in terms of, what I can do is I can replace the limits of integration by just substituting them into my substitution. What do you say? Substituting in your USub? Yeah, we can do that. So I'm taking this piece and I'm saying when x equals, who's my upper limit? X equals 2. U should equal 2 squared. So that's 2 squared plus 1, which 2 squared plus 1 is 5. Also, when x equals 1, I get u to equal 1 squared plus 1, and that's equal to 2. So what I can do is take those limits of integration, and if I've changed everything to u, I replace them back in. So what does that look like? I've got to now color code a little bit. I'll try to use orange or something. Upper limit's now a 5, lower limit is now a 2. And so now what I can do is integrate as usual. I get an answer. So let's have fun with that. We still have the 1/2. When you integrate u to the 5th, what do we get? U to the 6 over 6. Yes. And who are our limits of integration now? Not 2 and 1, they are 2 and 5. We have to be careful because we had to replace them. And now, if we do that, no problems. What do we get? 1/2 times 1/6 is 1/12. We'll pull that out of the situation. And now we're going to use the fundamental theorem of calculus to help ourselves out with the u to the 6th. So I should get something like 5 to the 6th. 5 to the 6th, subtract off 2 to the 6th. I'll write that in. So if we actually want an exact answer, I'm moving sideways. Yes, use your calculator. 5 to the 6th, 5 exponent key 6 is 15,625. 2 to the 6th, 64. So if we use our calculator to do the subtraction, what do we get? 1/12 times 15, I'll double check. 15561. 15561. And just check, I'm curious, I don't know off the top of my head, but if I were to see if that reduces, it ends up reducing. Wow, look at us. So what we end up getting is 5187 over 4. And we end up having the answer. So personally, for the most part, I think that when you do a USub and you have definite integrals, it might be quicker just to put in the limits of integration in terms of u, and then I guess it's a little less complicated to have to do the math to get the actual number. But there is another way if you are like totally against this, and I know there's a lot of things in math where you can't totally be against because there's no other options, but I'm here. Let me give you an option. So one other option, a little note, and sometimes we tend to choose whether or not we want to replace the limits of integration at the beginning or at the end. Sometimes with experience, certain problems take different techniques to be easier. So with experience, see what works for you. But a little note, if you don't replace the limits of integration at the beginning. So if we don't do this at the beginning, what's our problem going to look like? Let's go back. Problem looks like, okay, so we had 1/2 u to the 50u. Okay, so integral of 1/2 u to the 50u. So what you could do at this point, remember, don't write the limits of integration down there in terms of x, so that would be incorrect. You could evaluate it as if it were an indefinite integral. Okay, so if you did that, we'd have 1/2 u to the 6th over 6 plus c, because it's indefinite at this time. But now what happens is you can say we still have to resubstitute in. So remember, u was not the original problem. So we simultaneously, what do we have? 1/12, that has not changed. But instead of u, what ends up happening? What do we call u again? I gotta look at that. X squared plus 1. Okay, so we still have this x squared plus 1. Sorry, I'll move a little higher for you. My fault. Okay, so now you're in terms of x, and now you are allowed. So now we can, how do you say, reintroduce our limits. Now write in the limits. So what does this look like? We no longer need that c anymore. We have x squared plus 1 to the 6th, but now we're evaluating at what were the limits based on the x, 2 and 1. And then if you want to take it through, you're saying, oh yeah, I mean, it's the same thing. What do we get? 1/12. Fundamental theorem of calculus says we're taking x squared plus 1 to the 6th minus another x squared plus 1 to the 6th. And what were those limits of integration? 1's 2 and 1 is 1. And so when we do the math on this, you'll start to see, what do I have, 1/12? Still, well, my friends, what is 2 squared plus 1? 5. 1 squared plus 1, 2. Look familiar? Maybe not yet. Just as we suspected. Well, maybe I zoomed in way too far away, but you are ending up getting the same problem. So whether you do this at the beginning or the end, it's still going to affect it. So the answer still ends up being, what, 5187 over 4 eventually. So kind of do what you feel is more comfortable for you. Personally, when I'm in Calc 1, most of the time I'll just get rid of the limits of integration, and I'll use the U versions right away, so I don't forget, because that's what happens. Usually our brains are so concentrated on other things that we end up forgetting to resubstitute at the end, and so might as well kind of keep that notation at the beginning. So having said that, let's do one more, kind of like what we did earlier. Very familiar. One last problem, at least for this part, and then I'll show you another trick that I know they don't really go over it, but it's something that might be useful if we approach integration later. So you get a little extra bonus explanation too. So again, looking at this integral, definite integral from 1 to 2 of x times x minus 1 with a radical, you kind of notice, yeah, there's complication going on. If we want to rewrite it, might save ourselves some time. That's x times x minus 1 to the 1/2 with the dx. And that's true. We'll let the u equal the x minus 1. And then we notice that we did this problem already. Du is dx. But if you remember, we've already integrated this, but the way we're seeing it is the issue with us, when I'm looking at this, is we still need a factor of x. So that's when the trick came to be, that we solved for x and we made x equal to u plus 1. So we're redoing it just in case. So we had this going on. So if we were to do that, what happens? If x is u plus 1, you can replace it. I'll write it in, u plus 1. And then didn't we have the u minus 1 as well? So x minus 1. So x again is u plus 1. So we had the minus 1 there. Still taking the 1/2 power. And then this is where we have to kind of be careful about, is that our dx is now du. So we were in good shape. We had this. You want to clean it up a little bit, but now that you replaced everything in terms of u, now we need to replace the limits. Either now or later, but might as well do it now before we forget. Once everything's in terms of u, your limits of integration have to be in terms of u. So this is where we're saying if x is u plus 1, u is x minus 1. When x equals 2, u equals 2 minus 1, which is 1. When x equals 1, u equals 1 minus 1, which is 0. And that makes me happy. I like when I see 0. Well, what do? We still have to go through the whole integration process. So I have from 0 to 1, u plus 1, and then I think we had u to the 1/2 du. And then eventually, I know we took a few more steps for this. We distributed the u to the 1/2. But at the end, just so that you all can see this, we ended up getting, after the integration, 2/5 u to the 5/2 plus 2/3 u to the 3/2. But we have to remember we're evaluating all of this on 0 to 1. That's the new part, just so that you're not confused. That was this integral. So you can kind of go back and then check from there. So if we have this, what are we doing is we replace the u with the 1. So I have 2/5 times 1 to the 5/2. And that's nice though. And then plus 2/3, 1 to the 3/2. And we're noticing, oh, that's going to be nice in a second or so. So fundamental theorem of calculus tells you to plug in 1 to that situation. And then what happens is you're subtracting off when you plug in 0. Well, what happens when you plug in 0 to both of those situations? No matter what, you get a 0 back. So that's nice. You don't have to worry about that second piece now. So we do a little bit of math, clean it up a little bit. 1 to the 5/2 is still 1, so we have 2/5 plus 2/3. You can use your fraction key to help you if that's something, because your brain is already shot, because we've been thinking all about USub all day long. So I got 2/5 plus 2/3. I add it, it's 16/15. Voila. So like I said, I prefer, at least in Calc 1, I'll replace the limits of integration in terms of u right away so I never forget. And actually it worked out to our benefit because we got 0 as a lower limit, and that's always nice. But if you wanted to change your mind, you say, I want to replace them at the end, no problem. You'll notice that when you get your final answer, where was it? I'll switch over here. You would then have to plug in x equals 2 and x equals 1, and you're still going to get it no matter what. But the more you practice, the more experience you will get. So this is pretty much at this point, through the example we just did, that should get you through section 4.5, but a little bonus explanation for you, I might be able to save you some time and some work, is that symmetry on functions, even though we haven't talked about it since I believe it was chapter 3. Whenever you can identify if something's even or odd and you notice that there's some symmetry going on with the limits of integration, it saves us a little time. So if I could kind of help, just kind of review with me. One last item, couple last items. If f is even, that's always telling us that every time you plug in negative x for x, you get the original function back. It reminds us that whenever you have an even function, you're symmetric about the y-axis. What do they call this? Reflection symmetry. And so example, some nice ones that you might like. What's our favorite function is y equal x squared. And she kind of noticed, oh yeah, y equals x squared, symmetric about the y-axis. What's another fun one? Pull up some trig for you, y equals cosine x. I gotta take my time to draw it, but it does have a nice symmetry going on. So whenever you see these, it's quite a nice shortcut for integrating. Let me kind of show you what's going on. And actually, I'll take that cosine function and I'll draw it a little nicer for you. Maybe I use the graph, we'll see. Let's draw this a little prettier. It doesn't have to be cosine, but I'll try to. I'll do part of it at least. So let's see. I have something, maybe I'll end up over here. Okay, so for the most part, I have maybe the integral of cosine from negative pi to positive pi, perhaps. So kind of look at your limits of integration with me. See how we're going from negative a to positive a. So as long as we are symmetric about the y-axis, see if I can write these in. That's negative a, and we'll say that's positive a. If we're trying to talk about integrals, a lot of times you could relate it to areas dealing with the curves. And if you remember, area that is above the x-axis is positive in a sense. And then anytime we had anything below the x-axis, it would work as our, what is it, trash truck? We would dump it out. So what ends up happening, if you're trying to understand, well, don't these areas, if you're symmetric about the y-axis, instead of using a lower limit that's a number that you end up having to plug in, why don't you just take the positive version or the positive values of x and then multiply them by 2? So this is going to give us a nice shortcut for integrating. All they're doing is saying, let's take everything from 0 to a and multiplying it by 2. So that's if you have to do things by hand, it might help out. So feel free to explore it. It only works as long as you know your function is even, and then it kind of gives you an idea, oh, it's symmetric about the y-axis, and as long as your limits of integration are positive and negative the same number, then it will work out very nicely. So nice shortcut there. something to look out for. I kind of notice a lot of these with trig functions, sometimes conic sections, depending where they're centered. That could be something, or portions of conic sections, I should say. So along with even functions, the odd functions kind of come into play. So remember, if you plug in negative x and you get the opposite of f of x, you've got symmetry with respect to the origin. And then what do we call this? Rotational symmetry. Rotational. And so some popular examples that we've seen before, if I pull a power function in, a lot of times you guys, y equals x cubed. Or pull the trig function back into play, y equals sine of x. So maybe I have that one. Something like that. Well, that's probably not the prettiest version, but you know what I look at it. I think that this, if we kind of look at the idea that something is symmetric about the origin, what ends up happening, just kind of a, I'll take a quick version of sine of x really quick, a portion of it, and we'll see this a little bit nicer. But let's say we have the function, it does something like this. And again, we're going from negative a to positive a. Well, we use the same concept. We notice, oh yeah, well, area above the x-axis is positive, but if we're symmetric about the origin, the area below the x-axis neutralizes. So we kind of collect as much as we dumped out. So we end up getting a really, really cool shortcut for calculus 2. We can incorporate it more in Calc 2. I can give you something actually that's not in Calc 2. So what I kind of do is when I see limits of integration like this, you kind of see this? I'll give you a nice example. You can look at the symmetry of each individual term and then just dump off the odd functions. So like you can kind of play around with all of this. Each individual, I'll say term, and dump the odd functions. So I see a lot of trig integration in Calc 2, but we still see it in Calc 1 too. So if I were to kind of, I think I can throw this into the mix. A problem like this we can do quite nicely using what we already know, but I might kind of pay attention and say, wait a second, look at my limits of integration. And I'll try to highlight them maybe in purple. So you see how positive case, negative case, no matter what they are, pi over 4 to negative pi over 4, what we can do for ourselves is kind of look at what type of function do we have in x squared? That is an even function. What type of function do we have for odd? We have the x is odd, and so is sine of x. Well, what happens with odd functions? If you have the limits of integration that look like this term goes to 0, this term goes to 0, and now all you're left with is the integral from negative pi over 4 to pi over 4 of x squared, with respect to x, of course. And because it's even, remember that it's 2 times this. Oh, well, maybe I'll do this. I'm counting ahead of time. Okay. I'll give you an extra step. Sorry, I got excited. Now I can take this and just take the positive, the right side of the x-axis, multiply it by 2. Life ends up being a little nicer. Now you can integrate just like normal, x cubed over 3, but we're evaluating it from 0 to pi over 4. And when we do that, what do we have? 2/3. Then we fundamental theorem of calculus. Don't we have pi over 4 to the 3rd minus 0 to the 3rd? Which ends up getting 2 over 3 times pi cubed over 4 cubed. What is that, 64? Sometimes we got to use our calculator at the end. So if you want to simplify this a little bit more, what is 2/3 times 64? It is 1 over 96. And it's kind of a quicker way to find the integration. I encourage you, see if you want to take the integrals with the x and the sine x the way we're doing with example 7 all the way through, and you could kind of see like, symmetry, as long as you know if the function's odd or even. And what's really important is that you have to have these same limits of integration. You can't just invoke this whenever you want to. But it kind of gives you a nice shortcut if you're ever so inclined. So have fun at getting good at this. You're going to be fine. Once you practice these, we're going to apply integration to chapter 5, and we're almost set for Calc 1. So I will see you next section.